Good afternoon to all of you. Myself, Dr. Jagannath Samanta. My topic of presentation: VLSI implementation of Reed-Solomon codec for ultra-wideband application. So VLSI, all of you know that very large-scale integration, and basically in any type of electronics chip, if you see, there is a lot of within that there are just chips are there. So that chips, inside that chips, we are implementing all this chip with the help of these VLSI technologies. Okay, so within that VLSI chip, we know that the number of transistors will follow 10 at 20,000 to the 10 lakhs per transistor per chip. So basically in this topic I will discuss what are the different VLSI implementation technologies. So that will I will design the Reed-Solomon basically in digital communication systems. So that encoder and decoder I will design for the ultra wideband applications. So these are the outlines of my presentation. So I'll go introduction, error correcting codes, ultra wideband technologies, and what are the different design of compact Reed-Solomon codec. And I have proposed a optimization algorithm. Based on that, I can optimize the total area of the encoder and decoder. And I also implement this our codec with the help of the FPGA implementation tool. Basically, the Xilinx we can use in, and also the ASIC based tool. So error correcting code ECC, basically you know that in data storage and system and data transmission system, basically the coding, it is a very coding error correcting code. It's a very important to detect and correct the errors. So if you see for any digital transmission, so that means your mobile communication, when we are talking about through distance communications, okay. So that means when you are talking to the other your friends, so that means the digital data, whenever it is transmitting through the transmission channel or in different types of storage systems, if you see that due to some noise or interference, the digital bits, it will maybe change. Okay, so 0 may be replaced by 1 may be replaced by 0. So that type of different types of random and the burst errors will occurs. So under these noisy conditions, how we can transmit the digital data error free. So with the help of this ECC error correcting codes, basically the error control codes, where we can basically error detection and error correction can be done with the help of this ECC. So with noisy condition, we can easily transmit the digital data without error-free transmission. So basically, the error can be used in any storage system due to the some defects, dust particles, and the radiation, so that the error-free storage can be achieved. So ECC basically are used to detect and correct the errors and erasure in most of the digital communication and storage systems. So they are basically in communication and the storage system. So reliability will be enhanced by employing this ECC code. So various types of error correction code, that is the Hamming code, repetition code, product code, BCH code, Reed-Solomon code, Gole code, tree code, Tallis code, convolution code, turbo code, block code, LDPC, low density parity check code. So these are lot of error correcting codes are available in the in literature. So most in this work, I will discuss the RS code. That is the very important RS codec ECC that I will design in my work. So what are the motivation? How why I can use this RS code in my ultra wideband applications? So basically, you know that the VLSI implementation of ECC are highly desirable in data transmission and storage systems. So and today's you know that the chip size, we are day by day it is reducing, the area and power consumption is also very much less are required, low power applications, and the high speed of the, because you know that video transmission, so a lot of data we have to transmit, so speed is a very important factors. So to avoid this we have to design in this field. So, okay, So increasing demand for low complexity, high speed and low power communication systems. So that's why I also work in this. So efficient hardware implementation of the finite field arithmetic units. So finite field arithmetic addition, GF addition, Galois field addition, Galois field multiplication. So these are the very important GF field arithmetic. So to implement this RS codec, we have to require efficient implementation, efficient hardware structure we have to need it. Implementation of efficient encoder and decoder also challenging tasks to the researcher. So in this field, the people they are working on this field. So the efficient design of encoder and decoder is a very important task, because if you see the codec architecture, basically encoder and decoder, most of the time we will see that the encoder and decoder design, if we do in it effectively in terms of the area or in terms of the delay or the power consumption. So by reducing the area of encoder and decoder, ultimately you are reducing the codec architectures. So although lot of works have been done in this, so enough scope to do the further research also. So ultra wideband technology, UWB, basically it is a wireless communication standard that is well suited to short range application. It is generally used for 3.1 gigahertz to 10.6 gigahertz. What are the different application of this ultra wideband technologies? Basically for location tracking, and location tracking means suppose I can provide the precise location where your device is there. Okay, so for accurate location, we have to use this ultra wideband technology. For secure smart home, so for your digital lock key, okay, so that type of digital keys for the smart home that enable to door to unlock based on proximity. So that's on smart secure smart home. You can use also ultra wideband technology. Radar and imaging system, different ultra wideband antennas are effective to use the bandwidth in high data rate. And automotive applications, for the ultra wideband radar can be used to provide accurate data to aid for the daily living, assistant listing devices, wheelchair devices, whilst providing a secure connections. Other application of the ultra wideband application is well suited to short range applications such as PC wireless monitoring, camcorder, wireless printing, and the file transfer to portable media player. So these are the different applications of ultra wideband technology. So how I can design the design of a compact, basically RS 23rd17. Basically it is a if you see the dimension of 23rd, so this is nothing but the n value and the k value. N is the number of bits byte in the, it is a non-binary. Okay, so this n basically it is a code word name. Okay, code word name, number of in byte, and k is the message length, and it is also byte. For 23rd, so 23rd it is a basically a triple byte error correcting code. So that means here t is the error correcting code. So it will be 3. How it is coming? Suppose the d minimum distance d, here it will be n minus k. So d so basically t it will be n minus k by 2. So that means 23 minus 17 by 2, that is 6 by 2 means 3. So error correcting capability for 23rd 2017 RS code, it will be 3. So that means maximum 3 byte error can be easily detected as well as corrected. So that is, so during transmission, suppose if you have total 23rd bytes are there. So out of this, maximum 3 bit if it is occurring error, so in the transmitter side 100% correctly this 23rd 17 will correct the message signal, so the received signal from that signal we can get the actual message what if it's sent from the transmitter side. So that is very important. So now if I design an implementation of RS and another 3-byte error correcting code, it is a 4741. It is also used for the intelligent home networking systems. So basically here RS code, basically it was invented in the year of 1960 by the great I.S. Reed and the Solomon, two great scientists at the MITs, MITs. So they have invented this code. According to their name, this RS code is given. So basically RS code has a numerous applications for the wireless and mobile communication system, for the storage devices like CD, though it is a obsolete, CD, DVD, and hard disk, barcode, Blu-ray discs, all this type, and the satellite communication also it is used, the digital television, high speed modern modem. So these are the lot of application of this RS code. Basically this RS code are capable for correcting both random and the burst error correcting code. So basically, and it is required efficient. The decoding algorithm is also available for this RS code, and RS code parameters are suitable for reconfigurable architectures. So for the higher correcting bit, for suppose we are designing for t equal to 3. So if you want to design that t equal to 6, so the architecture will be reconfigurable. So this is basically the block diagram of RS encoder. So this block indicating this, these are the GF multiplier, and this plus sign is indicating GF adder, and all these are inside this. There are G0 to G2T. So these are numbers of constant GF multipliers are there. There is a two switch, gate 1 and gate 2. So basically, and you are giving the message bit here, message you are giving here, and finally you are getting the code word from this CX. So this switch during, so for NK, for NK, so that means during the K cycles, first K cycle, your gate 1, this gate 1 will be connected to this one B, and this will be closed. Okay, and now during n minus k cycles, so ultimate total will be k plus n minus k, that will be equal to total n. So that is the code word length. So during last n minus k cycles, gate 1 will be connected to A, and gate 2 will be opened. So that means first k cycles we are sending this message to the code word, and the next n minus k cycles we are getting the parity bits. So that is parity bit we are generating in the last n minus k cycles. Okay, so this is the block diagram of RS decoder. So we have already told that ECC basically in decoding portion and the decoder side. So there are two portions, one for the error detection and another for the error corrections. For error detection, that means whether during transmission any error occurs or not. So for detecting that, we need the syndrome cycle, syndrome block. It is very important. Syndrome block, it is you can see that this is the syndrome block. So this side for generating the error detection, and for error correction, if your error is detected, that means during transmission there are some error occurs. So that then we go for further. So that means which location error occurs and what is the magnitude of, because it is a non-binary, so magnitude on that particular location, what will be the magnitude. So that I have to find. So for that we have go for key equation solver. This is the very complicated block. Lot of decoding algorithms are available. After finding this is the chain search. That means which location actually error occurs. After finding the location and that particular location, what will be its magnitude. Okay, so finding after that location polynomial and the magnitude polynomial, we will find the error polynomial. So that means and if we add with this with actual data receive signal, so that if you see, suppose that is occur, and we are sending these things same value with error plus, that means receive signal with error. So here actually what is done, receive signal plus E cap. So this E calculated, this is calculated and occur, so they will be cancel each other. Okay, so that is the beauty of the error correcting codes. Okay, so similar Galois field, same value if we add, so that means 0 plus 0, it will be 0. So and 1 plus 1, just like a your XORing, so that things will also be there. Okay, so same value we are calculating error and calculated error, and the actual error occurs during the transmission, they will be cancelled to each other. So so that is the block diagram of RS decoder. Okay, so this constant GF multiplier, basically it is used in syndrome block, it is used in chain search block, and these are in Forney block. Okay, and finally error correction. So these are the, and your GF multiplier, GF general multiplier, that will be used in KS equation and the Forney equations, Forney algorithm. So these are the very important. So existing lot of this case for solving the case, there are a lot of decoding algorithms are there, but in our work we are basically focus on the modified RIBM algorithm. Okay, so these are, we can also represent in this way, but our main research we are focused on inverse P, Burley-Massey BM algorithm and RIBM algorithm. So that we are focusing. So GF arithmetic circuit optimization is very important. We have proposed a new optimization algorithm that has been proposed based on the common sub-expression elimination method, which reduces the area complexity in terms of the XOR to gate of the constant GF multiplier. And we also employing proposed optimization GF algorithm, design a compact Galois field constant and the general multiplier for ECC codec. So what is my proposed optimization algorithm? So in algorithm we have designed in the two direction, one is the forward direction and another is the reverse direction. So first step, if same combination of the four coefficients are found in two or more equation, then replace with a new variable. So that can be represented in numeric form. So in form, we are using the four variables, okay, and four loops we are using this. And the step 2, if same combination of the three coefficients are found in two or more equation, then replace with a new variable. Then you also, if same combination of the two coefficient found in two or more equation, then we replace with a new variable. Okay, so now fourth step, repeat step 3. If same combination of the two coefficients are found in any equation and replaced with a variable which is a part of new variable used in step 1 and step 2. And step 5, rest of the uncommon combination of the coefficient are implemented directly using the XOR to gate. Now in reverse direction we also do, these are the steps are similar, but we are considering the reverse way. So these are the steps, are 5 steps are there, okay, and the representation, mathematical representation we also. So now I'll show the some examples. So if you see that A, that is the decimal value of 126. So in GF2 to the power 8 field, so if we apply, find the 8 y0 to y7, they are equivalent. So without using the optimization, so directly if you use, total 37 XOR gate are required. But if I use, after applying our proposed algorithm in local optimization and the forward, then the total number of XOR to gate will be 23. And if the proposed algorithm is applied in local optimization in reverse direction, you will see that 21. So actually 37s are required. After forward direction it is reduced to 23, and after reverse direction it will be 21. So these are the diagram of constant GM multiplier. So these are the architecture we are using in. So if I show the theoretical complexity, if you, without for a your GF your circuit, okay, so the syndrome circuit for without optimization 123 gates takes up to gates are there. After applying the local optimization it is 87, and using the global optimization it is reduced to 54. So overall improvement 29.27, and here using the global optimization it is 56.10%. And for comparison of different in syndrome block, if you see that, so it is also reducing up to 20% and maximum 66.15% improvement we are getting. And for the general multiplier based on the Karatsuba algorithm, to optimize the Karatsuba multiplication algorithm, the product terms are split into two alternative forms and computed all the terms in the repeated fashion. Proposed multiplier need lesser number of addition compared to original Karatsuba multiplier, and the overall area of the uh, is reduced. And if we use this, so this diagram basically theoretical complexity of Karatsuba algorithm and modified Karatsuba algorithm for different GF field. So you see that overall improvement 30.57%. And if I use, this is the block diagram of architecture of the KS block using IBM, and if I see the complexity and we can compare with the existing work also, and we see that 7.65% improvement, and with local optimization and for global optimization it is 38.24% improvement. And for syndrome block we also use so 11.50 and 38.05 with existing improvement with existing works. So FPGA implementation we have also done, and here you can also see that delay is not changing. So delay is remain constant for after using our proposed optimization algorithm. Though we are showing that the area is also reducing, but without hampering the delay. And FPGA based, so this is the another result of 47 RS4741. It is also see that for using the RIBM, so all the 5 blocks total in a ACC codec, so their information we are giving, and ASIC based result also their result we are also giving. So this work basically we have designed a compact triple byte error correcting RS2317 a codec, and that is basically designed for the ultra wideband applications, and it is also that is designed for the your storage system, and RS4741 that is used for intelligent home networking system also. So these are the important published work. So this work is also published in SCI journal. So these are the references, and thank you.